Okay, so now let's go back to one dimension. We've been talking so much about rotations, like it definitely behooves us to understand rotations and angles extremely well. So let's remember about angles and rotations in 2D geometry. And just to warm you up, I'll ask you to try to remember, we'll get to this eventually, but you remember the dot product of two vectors? It has something to do with rotations, but why does it have to do with rotations? Why, if you just multiply these numbers together and add them up, why would that have anything to do with angles? Well, we'll remember. But first, let's go back to some basics. Okay, so we're going to talk about 2D rotations for a while. And remember, I've given you now a new instruction. I now let you have this new qubit instruction. I let you rotate by any angle. Okay, so we'll call it rotation by theta, and we'll use the mathematician's convention that theta is always counterclockwise on a qubit A. Okay, but I'm just going to write rotation sub theta as a shorthand and think of this as a linear transformation operation on 2 dimensions. And allow me to also remind you about radians. So here's the 2-dimensional plane. Here's the unit circle. And let's see. Let's say you have this vector here, and it's at angle theta. Well, you can measure theta in degrees. Let me also give a name to this. Let's say this is x, y. So x squared plus y squared equals 1. This is the unit circle. Let me add a few more things here. This is ket 0, aka 1, 0. This is ket 1, aka 0, 1. And we have this generic unit vector at angle theta. Now, the real mathematician's way to measure this angle is to just say, never mind about this angle. We're just going to look at the length of this. We're going to look at this length of this arc. I mean, the whole circumference is 2 pi, right? This is a terrible board. It's 2 pi. It's 6 point something. And so this is less than 6. But whatever this distance is, it's some distance, and that's also theta. Or rather, actually, they would say, a mathematician would say, we'll just measure this length and call it theta, and then we'll name this angle after this same amount. Okay, so for example, perhaps this is around 36 degrees, maybe. Then that means it's 1/10 of the way around the circle. So that means this distance is 1/10 of 2 pi, which is 0.6 something. Okay, so that's this angle in radians. And I also really like this convention. You know, as I mentioned before, there's these nerds on the internet who have the Tau manifesto, and they're pi is a dumb name. They should have just called this a letter, tau, and then this thing should have been tau over 2. I kind of like it because tau means 1 turn, all the way around. And so instead of saying oh, this is 1/10 of 2 pi, you're this is 1/10 of the way around the circle. It's 1/10 tau. So maybe I'll start doing that just to be weird. But anyway, tau stands for 6.28, all the way around a circle. Okay. So, yeah. So let's think about exactly this operation, rotation by, I don't know, this particular theta depicted in the picture. The angle such that this vector's coordinates are x comma y. And one thing we can do is try to remember what is the matrix for this transformation. We know that every quantum operation has a paths matrix or a matrix, or sorry, a paths diagram or a matrix. These are the same thing. And what is it? Okay, well, some matrix. And, this is a 0, 1, 0, 1. It's going like this. So if you have all your amplitude on 0, that's like saying if you are this vector, ket 0, where do you go to? Well, you rotate by theta, you go to xy. So it's x, y. And here, if you have all your amplitude on 1, or in other words, you are this vector here, 1, where do you go to? Well, you go to theta here. And I think you can see by symmetry, right? Like this distance, this horizontal distance here becomes the new height. So that's why x is down here. And this like vertical distance becomes like the new like width, but like negatively. So it's like negative y. Okay, so this is the matrix for rotation by theta. Okay, and it also has an undo or an inverse. Well, it's rotation by negative theta, of course. And you could think about like, rotation by negative theta would take 0 to down here. So that would be like x minus y, and it would take this one to over here, so that would be like y minus x. Did I do it wrong? No, I think this is okay. And this is also, as we saw, this is like the inverse of this, but since it's unitary, we saw in the homework, it's also this thing called the dagger, or the conjugate transpose. So it's really, you can also get it by like interchanging rows and columns here in this matrix. Okay, obviously, yes? I don't know why I wrote negative here. Thank you. I mean, like, everybody said, like, or something. Like, I was like, oh, there's got to be a typo somewhere. Thank you. Good. Okay. So these are our new instructions, rotation. And you might say, like, oh, if I know theta, what are x and y? Well, they are what they are. In some sense, by definition, x, this is sine theta, right? No, it's cos theta. Whoops. X is cos theta, and y is sine theta. This is x, this is y. That's literally the definition of what cosine and sine are. So this is just, by definition of the phrase cosine and sine, we have these facts. And so now that some trig is on the board, let me tell you the only fact about trigonometry you will ever need in this course, or some might say even in life. Here it is. If theta is small, then sine theta is basically theta. Okay, this is the only fact you'll ever really need in life. And why is this true? Well, you just have to like really like put a magnifying glass like right here in the picture, like just zoom in super closely to this part of the picture. Like you have this circle coming in, and like the origin is like way over here. And like, maybe this is like theta. Here's like ket 0. This is the axis. This is x, y. And the y is sine theta, right? This is sine theta. This is cos theta. And y is also like this height. And like, you're looking at this distance for the board. You can't even tell the difference between this line and this line, right? They're basically the same. So this arc length is basically the same as its height if this angle is like super small. So that's why that's true. And indeed, another small factor you can notice is that like if you want to get like real correct about it, this height is definitely less than the arc length, right? Because here, I mean, just imagine it like this straight line and like the curved version. The curved version is longer, which means that sine theta is actually not just basically the same thing as theta. It's actually always like a little bit less than theta, unless theta is 0. If you really want to know, this is off by something like theta cubed, but don't remember this. Okay, the things to know is sine theta is basically the same thing as theta, and if you really want to know, sine theta is always at most theta. Okay. So now, actually, the one reason that's very important in quantum to remember is you may find yourself with a qubit whose state is exactly this vector. It's the vector at angle theta. And then you might ask yourself, what happens if I do extract all, or extract on this qubit? It'll output either 0 or 1. And in this case, like x will be really close. The amplitude on 0 will be really close to 1. So probably it'll output 1. And the amplitude on ket 1, the height, is really small. So it probably won't output 1. Did I say that wrong? It'll probably output 0. It probably won't output 1. But how probably won't it output 1? Well, sine theta squared. And that's theta squared, around theta squared. So there's another fact to remember. if a qubit's state vector is at angle theta, okay, which we now know means it's like cos theta amplitude on 0 plus sine theta amplitude on 1. Let's just saying this. Well, and you extract, if you will, the probability that the output is 1, which is a very unlikely thing. If theta is small, let's say small, well, it's exactly this thing squared, sine theta squared, which is about theta squared. Okay, so if theta is like 0.1 radians, and then you measure that qubit, the probability it actually outputs 1 is like 0.01. And like, sounds weird to say, but we'll eventually see that the fact here that not only is this probability, like if the state vector is practically the same as 0, it's very unlikely that when you measure it, you'll see 1. It's not just that it's like very unlikely, it's like way unlikely. It's like the square. Like if theta is really small, theta squared is like super small. And somehow, it sounds weird, but like the fact that that's super small plays a major role in like quantum speedups and quantum algorithms. It's basically the reason that like Grover's algorithm for SAT works as well as it does. It's because this is like the square of theta rather than theta. But we'll have to see that a little later.